Okay, so now let's derive a conservation of energy expression that will be easier for us to apply to our problem and consequently solve our problem. So we've already come up with the expression that negative delta P is equals to delta KE. And that what that means is that a loss in potential energy, whether that's gravitational or spring potential energy, is usually manifested as a gain in kinetic energy. So the delta part, obviously, from mathematics means a change. So delta KE in this case is final kinetic energy minus initial kinetic energy. So those subscripts I and F indicate, final and initial values respectively. And the same goes for delta PE. So we have PEF minus PEI, which is your final potential energy minus your initial potential energy. Okay. So now if we substitute those new expressions into our conservation of energy expression that we found, then we end up with that last expression there. Minus PEF minus PEI, where the PEF and PEI are in parentheses, and then you have KEF minus KEI in parentheses, right? So um, here, now if we take out the parentheses, okay, so that we're able to, simplify this expression further, okay, so minus PEF. So of course, when we take out the second PE out of the parentheses, it becomes a positive value because you had negative, so it would be negative 1 times negative PEI gives you positive PEI. So this is the expression that we have. Okay, so if you rearrange the expression, meaning we collect all the initial terms together and the final terms together, then we end up with this, which tells us that the sum of the initial kinetic and potential energies is equal to the sum of the final kinetic and potential energies. And essentially, this is the law of conservation of mechanical energy. Okay, so now let's apply those concepts that we've just established to solve our problem. Okay, so again, we're told that the block arrives at C with a speed of 0.90 meters per second. And then we are asked to prove that the elastic energy stored in the spring is 670 joules. Okay, so we know that we're going to apply the law of conservation of mechanical energy. Okay, and specifically, the spring's potential energy, we can define that as our initial potential energy. So you can see in our law of conservation of mechanical energy, we have an initial kinetic energy and an initial potential energy. Okay, so since we're told that the mechanism of this um, sequence of events starts off with the spring being compressed. Um, as you can see that location H, the spring is compressed, and then once that compression ends, the block is released. So it accelerates forward towards A, okay, towards the section A, and then goes on to B, and then it goes up the ramp up until C, right? Okay, so we can definitively conclude that our initial potential energy in this equation is the spring's potential energy, which is usually given in that form, half kx squared. But we won't need to apply this equation because we don't have that information. We don't know how much the spring was extended by, so that we can plug in that x value, and we don't know the spring constant. So we have to work backwards. We have to figure out use the other forms of energy that the spring's potential energy was converted into to work backwards and figure out what the initial uh, potential energy of the spring was. Okay. Okay, so we know that once the block is released, it moves along the ramp, specifically first along the section of the ramp AB and then onto the second section BC, right? And because that ramp is frictionless, all the spring's initial potential energy is converted to both kinetic and gravitational potential energy. So along the section AB, it is just going to be purely kinetic energy because it's on the same level. The block is on the same level, so it just it jumps from the spring, and then all that is energy in motion along that section. But then along the section BC, it is going to go up a ramp. So that means it is going higher in the gravitational field, right? So, and how high it goes is determined by that height there that is given as 1.2 meters, right? Okay, so therefore, let's define, these quantities so that we can refer them. We can use that, we can apply that law of conservation of mechanical energy. We know that we already have an initial potential energy. Okay, so what is the initial kinetic energy in our equation? It is zero because the spring is stationary before it is released by the spring. So we need to look at it from the perspective of not when the person is applying the pushing force. So we are looking at it from the perspective of from when that block is already compressing the spring fully. Okay, so now there it's just it's smushed the spring to the very end, and then somebody is saying on your marks, and then get set, go. So from that point where we say go, that's our reference point. Okay, so at that point, the initial kinetic energy of the block is zero. It starts from zero velocity. Okay, and then the block's final kinetic energy will be the speed that it has at point C, right? Okay, and that is given to us in the question as 0.90 meters per second. Okay, and we also have the fact that it's going to gain kinetic energy along that section between B and C. Okay, and we know the potential energy equation is mgh. Okay, and our h value here is 1.2 meters. Okay, so let's put that all together then. Okay, but before we do, just notice that that block's gain in gravitational potential energy is only attributed to that height, 1.2 meters. Okay, you might have a little bit of doubt about this because you're saying that it's moving along a diagonal ramp. So it's not as if it's just being lifted directly from the ground and going up H. So you're going to ask perhaps, doesn't that angle of the ramp contribute something towards the energy change? No, it doesn't, because the key thing here is that this ramp is frictionless. So that means it doesn't lose any energy in other forms, like as it's going along that ramp. So the length of that ramp normally would affect how fast it goes up that ramp, especially if there is, if that surface is coarse, right? So it'll slow it down. But in this case, because it is frictionless, it will rise up the gravitational field just as fast as if it was raised from the ground up. Okay, and that might seem a little bit counterintuitive, but perhaps an example that I could think of would be, for instance, if you have a roller coaster somewhere, and then that is stationary above the ground somewhere, and then it is released and it goes down this track that is completely frictionless. If you had another roller coaster at the same point, and let's say it was just hanging up above the air, and you released it to fall under gravity, it would arrive at the same point. At the same time as the other roller coaster that is going down that ramp, even if that ramp was sort of like diagonal, because the ramp or the track is frictionless. So, and that's a very neat thing, right? So that's why we can make the conclusion that the gravitational potential gained by this ice block is just purely determined by that h value. It has the ramp, the length of that ramp doesn't affect it, right? All right, so now we can prove that the spring's initial potential energy is 670 joules, and we're going to apply our conservation of mechanical energy expression. So note that PEI is our unknown. So we know that we should be getting approximately 670 joules, but now we're trying to solve for it as if we did not know that value, right? So let's apply the concepts that we came up with in the previous slide. Okay, so we know that our initial kinetic energy is zero. Remember, the spring was compressed and we assumed that that was stationary. Okay, so before it was released. Okay, so that's why we have our KEI value as zero. And now our PEI value is our total mechanical energy before, um, you know, in our initial phase, let's call it that, right? So I represents initial, right? So the total mechanical energy, since there is no initial kinetic energy, it just consists purely of this spring's initial potential energy. So all that is converted to our final phase, which is the kinetic energy of the block as it is moving along the ramp, okay? And oh, not when it's moving along the ramp. Let's be more specific because we are just pinpointing 2 points, right? So they're asking us, so that initial potential energy is converted to the kinetic energy that it has at point C and the potential energy that it has at point C. So that PEF, note it is obvious what kinetic energy is, but the PEF could, just because we have studied both gravitational potential energy and spring potential energy, and in this question we have both, right? So this PEF could have consisted of some spring potential energy, perhaps in some world, but it only has gravitational potential energy. The only potential energy that is relevant at point C is gravitational potential energy, okay? Even that PEI value in another case could have consisted not just of the spring's potential energy, but it could have also had gravitational potential energy. So that PEI could have encompassed two kinds of potential energy. So in case I have lost you there, so just think of perhaps a question where, or a scenario. Let's say you have a toy car that's operated on a spring, and then it is placed on top of a ramp. Maybe it's like some kind of toy car set, right? So that toy car is wound, the spring is wound, and then it is, since it's placed above a certain height above the ground, it will both have spring potential energy and gravitational potential energy, and that is going to be transferred to kinetic energy, etc., etc. So, but in this case, we have a simpler case. We just have our initial potential energy just consisting of the spring's potential energy, and then our final potential energy just consisting of gravitational potential energy. Okay. All right. So now let's move on then. So we can substitute now our uh, values, okay, that we have been given into the formulas for kinetic and potential energy. So kinetic energy is usually given as half mass times velocity squared. So the mass of our block is 55 kilograms, and the speed or the velocity of the block at point C 0.90 meters per second, not 0.0.9 meters per second squared. That's a typo. And then our block's potential energy is just going to be given by its height above the ground, which is 1.2 meters. So it's mass times gravity times height. Okay. So once you evaluate those, so specifically the kinetic energy gives you 22.275 joules, and the final potential energy is 646.8 joules. So summing those together, then you end up with approximately 670 joules. So we have proved that the initial spring's potential energy, which is converted to kinetic and potential energy, is 670 joules.